Hi all, Professor Monty here. Today we're going to do two different sections. We're doing 1.7 and 1.8. So let's get started. 1.7 is called the chain rule. And what the chain rule is, the chain rule is used to take derivatives of composed functions. So the chain rule, if it's a composed function, and remember a composed function is one function inside another. In algebra, we would write a composed function this way. We would do either f of g of x, but that's not really going to help us for our purposes. Typically, we would see it as f of g of x. And that function g of x is inside the f function. So as an example, we may have, say we've got a function, we'll call it capital F of x, and maybe it's x squared plus 3, that's a function. But it's inside another function. Say that's inside the fifth power. So that's two different functions right there. One of the functions, in our case, x function, would have been the x squared plus 3. And the f of x function would be the x to the fifth. Because notice what we're doing is if we're doing f of g of x, we're taking this g of x function and replacing it right there where the x is. So once we compose those, let's make this look a little bit more like a fifth power so you don't think it's a third power. So when we compose that and we plug that x squared plus 3 in where the x was, it becomes x squared plus 3 raised to the fifth. So that's what I mean about a composed function. So again, one function is inside another function. So when we're talking about the inside function, well, that's obviously this function, the x squared plus 3 was inside the x to the fifth function. Okay, so it's important to recognize what we're talking about, an inside function. So let's talk about the rule first. What I'm going to do is I'm going to show a problem that's a composed function. We're going to look at it and we'll multiply it out, take the derivative so we see what the derivative should be. Then I'll talk about the chain rule, and we'll use the chain rule to see we get the correct answer. So here's some examples of composed functions. So let's see, we may have, let's say f of x. We may have the square root of 3x minus 4. That's a composed function because it's not just the square root of x, it's the square root of a whole function, the 3x minus 4. Or maybe g of x is something like we just did. We could say 5x squared plus x minus 1 all raised to the 7th power. So instead of just x to the 7th as the parent function, we have another function, that 5x squared plus x minus 1 inside there. We're also going to see them coming up in the next chapter. Maybe we'll have e to the 4x plus 3. So that exponent, we usually wouldn't put it parentheses there, but that exponent would be the inside function. We're going to find out how to find derivatives of exponentials in the next section. But that's what I mean about inside functions. We got something inside another one. And we'll often see parentheses. Maybe we don't see parentheses as in the example of that e to the power, but we could put a parentheses there. We don't see that square root as a parenthesis, but notice we could write that as inside parentheses 3x minus 4, all raised to the 1/2 power. Okay, so let's look at one that we can actually multiply out first. and then I'll show you the chain rule. So the chain rule looks like this. Chain rule, it says, if I've got some function, let's say f of g of x, as we stated before, but what I want to do is I want to take the derivative of that. Remember, if I put that d dx on the outside, it says I'm taking the derivative of something. So if I take the derivative, what I get is I take that derivative of the f function, the outside function, leaving the inside function just as it is. But then the chain rule step says, then I multiply it times the derivative, whatever that inside function was. That piece I'll refer to as the chain rule. Don't forget the chain rule. Okay, so that's what it looks like. If we wanted to write it a little cleaner, maybe I'd write something like, if capital F of x is f of g of x, so that we're not confused with that d dx notation, then f prime of x is f prime times g of x times g prime of x. So notice that g of x inside just stays exactly as it is. And again, this piece out here, chain rule. Okay, so there's my formula. However you want to see it, it's just the derivative of the outside function times the inside function, or with the inside function composed, not multiplication, excuse me, times, there's my multiplication, the derivative of the inside function. Okay, so here's what I was talking about before. Let me show you an example. This is just straight out of the book. It's problem 2, and they give us y equals parentheses 2x plus 1, there's our inside function, squared. And the reason we're doing this is because we can simplify this before we take the derivative. That's squared on the outside means we have 2 of these multiplied together. Again, I'm going to FOIL it out. Hopefully you can do this in your head by now, but if not, 4x squared plus 2x plus another 2x from the inside plus 1. And so that gives me, those of course add together, I get 4x squared plus 4x plus 1. There's my function, that's y. If I take the derivative y prime, I get 8x plus 4. Done. Okay, so I did all that correctly. I know that's what the derivative has to be. Let's apply the chain rule instead of multiplying it out. Make sure we get the same answer. So we'll say using chain rule. So I'm showing this similar to what I did with the product and the quotient rules. So if you look at my video on sections 1.6, you will see the product rule and the chain rule, and I do a similar thing where I multiply it out or I divide, and then we use the appropriate rule to see that we get the same answer. So that's the same idea we're doing here. So using the chain rule, my original function y equals 2x plus 1 squared. Remember what I do. So the outside function would be something squared. So I've got this squared function. When I take the derivative, I bring this 2 down like I typically do. I'm going to erase that because I don't want that written up there to see when we look at it. But it's 2 times that 2x plus 1. Remember, we just leave that alone, and then I drop the exponent by 1. So if it would just had been x squared, I'd say, oh, it's 2x to the first, or just 2x. Well, that's what I have. But then I say, wait, I haven't done anything with that inside function yet. Now I have to multiply by the derivative of the inside function, which is just 2. So this was the derivative of the inside function, or the derivative of that 2x plus 1. That's where that 2 came from. That's the chain rule. And now this 2 on the outside here, I can multiply by this 2. And notice what I get is y prime is 4 times 2x plus 1. Wow. And if I just multiply all that out, I distribute, I get 8x plus 4. Oops, forgot my x. 8x plus 4, which, check, it is the answer from above. So that's the chain rule. We'll do a few examples of this so we kind of get a better idea of it. But again, it's something once you practice, and this is something that you're going to see the chain rule for the rest of the semester. So do bear that in mind. Sometimes we'll see some things that are like, oh, we'll see it in this section because it's an application or it's whatever, and we may not see it ever again. Chain rule, product rule, quotient rule, we're going to see the rest of the semester. Okay, so let's jump into problem 4. And again, this is one of those, that problem we just did. Problem 2, you may say, well, why don't I just FOIL it out first? That's easier, and then I can just take the derivative. Well, look at problem 4. Problem 4 says y equals 8 minus x, that's my inside function, but it's raised to the 100 power. I don't want to write 8 minus x times 8 minus x times 8 minus x 100 times and try to multiply all those out. That would, of course, just be ridiculously hard. And then I'd have to factor it out at the end to get the correct answer. So what I do is I do the chain rule. Remember the chain rule, we bring that 100 down just as if it was x to the 100th. If it was x to the 100th, we'd say, oh, it's 100x to the 99th. Well, we do that. It's just not an x, it's an 8 minus x to the 99th power. But then I say, wait, I didn't do anything to the inside. I have to take the derivative of the inside function. That's the chain rule. Oh, the derivative, that's just -1. Remember, the 8 goes to 0, the x goes away, so it's -1 instead of minus x. Again, that piece was the derivative of the 8 minus x. And now I just multiply the -1 times the 100, and I get -100. 8 minus x to the 99th. Oh, awfully quick and simple. So these, once you understand what you're doing, quick to do. It's no big deal. Just remember, if there's stuff inside the parentheses, inside some grouping, we have to multiply by the derivative of the inside. All right, so let's jump on to another one. This problem 16. A little bit harder. We've seen the simple idea of doing these. Next is just you have to practice and make sure you get them down. But this is 7x to the 3rd is the numerator. The denominator is 4 minus 9x to the 5th power. Now, here's what I notice. On the top is not a composed function because it's just all we're raising to the 3rd power is just x. Not 7 plus x, all raised to the 3rd power, nothing like that, just x to the 3rd power. But on the bottom, it's not x to the 5th power. It's 4 minus 9x to the 5th power. So when I take the derivative of the bottom, I need the chain rule. When I take the derivative of the top, I do not. So let me put a little arrow here. This is not composed. There's no inside function. This is composed. So we'll need the chain rule to take the derivative. All right. So that's what I'm looking at when I do this. Let's go ahead and take the derivative. I have to use the quotient rule because it's a quotient. So here, let's even say it. Here, let's erase that. Let's remind ourselves, we have to use the quotient rule. Again, if you haven't looked at my last section, that's quite an E. If you haven't looked at my last section on the quotient rule, we have a little saying for it, but it goes low D high minus high D low, square the bottom, and away we go. That's my quotient rule. So I'm going to apply that on this problem. So let's see. So we've got y prime equals, okay, so it's low 4 minus 9x all raised to the 5th, d high, that's 7x cubed when I take the derivative, 21x squared. That's the end of that piece, minus high d low. Now, on the bottom, when I take the derivative, I have to bring that 5 down. It's going to go 5 times 4 minus 9x. Let me rewrite that 4 so it doesn't look like a 9. 4 minus 9x to the 4th power, but then times the derivative of the inside, the -9. That's my chain rule piece. Chain rule. And then it's all over the bottom squared. Notice I'm not multiplying out the bottom, I'm just saying the bottom squared. Now, we're gonna clean this up a little bit. And what I'm gonna do before I multiply out each of the two factors on top, I'm gonna clean it up. So let's see what I can do. So let's see, notice greatest common factor. 7 goes into both of those numbers. X squared goes into both of those numbers. 3 goes into the 21 and the 9. And they both have a 4 minus 9x to the 4th. Good heavens. There's a lot of stuff I can factor out. Now, let me show you. I'm going to multiply it out as is before I factor. It'll make it a little harder to factor, but that's okay because I want you to see what it looks like just condensed, multiplied out before we reduce. All right, so I've got that. I don't know what happened there. That's not even this section. Here we are. So we've got that 21x squared times 4. Move that up so I don't keep hitting that with my finger. 9 minus 9x, 4 minus 9x to the 5th. And then this minus here and this minus here are going to cancel each other out. We'll get a plus. Let's see. We have 7 times 5 times 9. 7 times 5 times 9 is 315. X to the 3rd times 4 minus 9x. What do we have? 4th power to the 4th power. All divided by 4 minus 9x. Remember, I multiply exponents. 5 times 2 is to the 10th power. This is the derivative. I haven't done any algebra. I've just simplified the top. Some authors will let you keep that as your answers. Sometimes they won't, and they're going to factor and reduce. Let me show you. I'll walk you through the factoring here so that you can see it. So y prime equals. Now, I'm going to pull out the greatest common factor in each of these two terms. 21 goes into both of those. So I can pull out a 21. Let's see, the 315, because the 20, it's just going to be 21 times 15. 21 times 15, yeah, that's 315. So I factor out a 21. Let's make that black. I factor out an x squared from both of those. And they both have a 4 minus 9x at least to the 4th power. All right, let's see what's left. I took out the entire 21x squared. I took out 4 of the 4 minus 9x's. There's 1 left. We could say to the 1st power, but we don't need to. When I factored the 21 out of the 315, I got 15. So I have plus 15. I factored an x squared from the x to the 3rd, so there's still 1 x left there. And that 4 minus 9x to the 4th is already factored out. So that's all that's left there. And this piece actually simplifies. The 15x minus 9x is 6x. So it's really 6x plus 4. And it's all divided by this 4 minus 9x to the 10th. Now, that 6x plus 4, I don't want you to think that's, let's do this. I don't want you to think that that's a division. This stuff is really 6x plus 4. Okay, we'll do that. I think that'll help. Because now what I'm going to do, so this is going to be one of my factors. That was this piece. So I'll cross that out so we don't think that's an addition to it. Okay, so we've got all that. Now what they're going to do is they're going to say, hey, these 4 cancel with 4 of these, leaving 6 of them. And then that's going to be fully reduced. So a lot of authors will put the answer as 21x squared times 6x plus 4, all divided by 4 minus 9x raised to the 6th power. Now, obviously a lot going on there. And there was just one little piece that had the chain rule in it. But a lot of that wasn't a chain rule problem. It was just a simplification. It was just an algebra problem. And it depends. Some authors, that first box that I have, they'll accept that. I don't know if we've got one that's crazy like this on the homework. I don't know what they're going to accept. I'm guessing they're going to simplify it all the way down to what I have as that bottom box. All right, let's try another couple of these chain rule problems. So let's go to 18. Now here, let's just throw in a simple chain rule problem along the way before we do 18. Say I've got f of x equals, let's do really simple. 4x plus 3 to the 5th. The derivative of that, I bring down the 5, leave the 4x plus 3 to the 4th power, but then times 4 from the chain rule, that's the derivative of the inside. So it's the 4 times 5 is 20, and then 4x plus 3 to the 4th. So just to show you that the chain rule part itself can be really quick, although it might be buried in with, like the last problem had a quotient rule. We'll see what happens on this next problem. So the next problem I have picked up is problem 18. F of x is negative 3x times 5x plus 4 raised to the 6th power. Now, to take the derivative of this, I have to use the product rule because that negative 3x, and notice that other piece has an inside function. The 5x plus 4 is the inside function. So this is product rule. And remember the product rule, first times the derivative of the second plus the second times the derivative of the first. All right, let's do it. So f prime of x. Now, when I say that, I'm using this to be f and this to be g. Okay, and by g, I mean the whole thing. So this is f, this. All right, so let's take a look. So it's the first, negative 3x, times the derivative of the second. We'll bring the 6 down, times 5x plus 4, to the 5th power, times 5 from the chain rule. That's the derivative of the 5x plus 4. So that was the derivative of 5x plus 4, the inside function. So there's my first times the derivative of the second, plus the second times the derivative of the first. Now this is nice, no bottom squared, anything like that, any craziness. So if I simplify, so I'm multiplying the negative 3x and the 6 and the 5. So what's that? 5 times 6 is 30, so negative 90x times 5x plus 4 to the 5th minus 3 times 5x plus 4. I'm going to leave it this way, although I will factor that out as well. Oops, to the 6th power. Almost forgot that. Now, if I factor that, what's common? Let's see. 3 goes into both these. In fact, negative 3 goes into both of those. So I'll factor out a negative 3 and a 5x plus 4, the smaller power, so to the 5th power. See what that leaves me. If I factor the negative 3 out of the negative 90x, it gives me a positive 30x and then that 5x plus 4 to the fifth's gone. I factored out the negative 3, but I still have one of the 5x plus 4's left. So it's plus, because I factored out the negative, 5x plus 4. Well, these two just add up, and so my answer, factored out, we'll say, I won't say simplified, but factored out, all that to the 5th, sorry about that, but then times 35x plus 4. That's fully factored. And again, fully factored is good, because if I was going to set this equal to 0, which I have to do if I'm going to maximize or minimize the function, I need it factored out to find out what values would make this derivative equal 0. All right, so a little more practice with the factoring. Another chain rule problem. Let's look at one more, and then I'll do an application. And then we'll jump into the second section we're going to do today. So here's 26. A lot of examples. Hopefully that helps you out, so that when you get some of these problems, you know what you're doing. This time, it's 2x divided by x squared plus 1. That whole thing is the inside function. That's raised to the third power. So this time, the chain rule, the inside function, the chain rule is going to have to be a quotient rule. So I take the derivative. Let's think how I do it. I bring that 3 down. Then it's times all this stuff to the second power. But then times chain rule, the derivative of the inside. Ugh. The inside's a quotient. I have to use the quotient rule. I'm going to write it up here. Low d high minus high d low. Square the bottom and away we go. All right, let's try it. So it's low d high minus high d low. Square the bottom, and away we go. Now what I'm going to do off to the side is clean this up. And the reason I want to clean it up so that everything doesn't flow down and get us confused, but let's clean all this up. So if I multiply out the top, I go this way, I'm going to get 2x squared plus 2 minus 4x squared, all over x squared plus 1 squared. That's equal to the 2x squared minus 4x squared is negative 2x squared plus 2, all over x squared plus 1 squared. Let's do this. I'm going to do one more step. I'm going to factor out that negative 2 out of the top. It's going to leave me with x squared minus 1. Good heavens, that factors 2. We'll factor that later if we need to. I don't think we need to. Okay, I'm going to replace this. I'm going to put it in where we had that. So my derivative becomes f prime of x. 3, now I'm going to do a little trick here. This squared, I'm going to make it 2x squared over x squared plus 1 squared. I'm going to square the top and square the bottom. You'll see why very shortly, because this is going to become a negative 2 x squared minus 1 over x squared plus 1 squared. Now I'm just going to multiply stuff together. So f prime of x, nothing reduces. I could factor the top. I'm going to factor the top for fun. I know you think that might not be fun. X minus 1, x plus 1, that piece. So when I multiply everything out, I've got the 3 times negative 2, which is negative 6. Don't want to do this. This piece right here, when I square it, is 4x squared. So instead of the negative 6, I've got the 3 times the 4x squared times the negative 2. So 3 times 4 is 12. times negative 2 is negative 24 x squared times x minus 1, x plus 1. All divided by, these are the same thing on the bottom. I add the exponents to get the fourth power. Nothing reduces, but there it is all factored out pretty. Again, kind of an ugly problem, but I want to give you some ugly ones so you don't just see them on the practice problems and think, oh, he never did any of these. All the ones he did were super simple. But as teachers, we run into that dilemma. Do I just want to show them the simple ones so that they see what the idea is? Or do I want to show them some more complicated ones so when it gets more complicated, they have seen examples? But a lot of times you see the more complicated ones, you say, oh, this quotient rule is really hard. It wasn't really the quotient rule that was hard. It was the algebra that was a little difficult. Okay, so anyway, that's the idea there. That's why I wanted to throw in that one really simple quotient rule problem. Not quotient rule, the one little simple chain rule problem to get those going. Okay, now let's jump into an application. I have an application that I've already pulled out for us. We paste it in right up here. Total revenue. And notice there's an inside function because inside the square root's not just x, it's a whole function. Total revenue function is given by r of x is 1,000 times the square root of that. R of x is the total revenue in thousands of dollars from the sale of x airplanes. Find the rate at which revenue is changing when 20 airplanes have been sold. Remember, when they say the rate change, that's the derivative. So what this question's saying, find the rate of change of revenue when 20 airplanes have been sold. They're saying find R prime, the rate of change of revenue, at 20 airplanes. So that's the question, R prime, and then plug in 20. So that's our goal here. We know the revenue function R of x is 1,000 times the square root of x squared minus 0.1 x, which can be written as 1,000 times x squared minus 0.1 x to the 1/2 power. Okay, so there's my function. I want to find the derivative. R prime. Now that constant multiple, it stays. Sorry, I wrote it as 100. So that stays times, oops. Then I use the power rule to bring that 1/2 down. 1/2 x squared minus 0.1 x to the negative 1/2 because I subtract 1 from the exponent. But I haven't done anything with that inside function yet. So I have to say times the derivative of the inside, 2x minus 0.1 from the chain rule. That was the derivative of the inside. And that's it. Now, usually we'll simplify these and say, oh, 1/2 of 1,000 is 500. We don't really need to if we don't want to at this point, because I'm just going to plug all this into my calculator. So R prime of 20, now I just plug in 20 wherever you say an x. 500. 20 squared minus 0.1 times 20 to the negative 1/2 power times 2 times 20 minus 0.1. And I'm pretty much just going to put it in my calculator the way you see it. I have to raise the power. On my calculator, I have to actually put that in parentheses. But everything else is pretty much just the way it is. I don't do 0.1 parentheses 20, I just say times 20. But I'm going 500, I'll tell you exactly what I'm putting in. So 500 parentheses, 20, and then the squared button, minus 0.1 times 20 close the parentheses, raise to the power, and I have to put parentheses, -1 divided by 2, close parentheses. There's my exponent. And then again, another parentheses for times, 2 times 20 minus 0.1. And you can close parentheses or not, it does not care. And then when I hit equals, I get 1,000 and it's 0.00. I'm going to do this. I'm not going to do that. I'm going to do it in black pen, 1,000.003. And the reason I'm doing it to 3 decimals is because notice up here, it says the revenue is in thousands of dollars. So that's in thousands of dollars. So what I need to do is I need to multiply it by 1,000. Thousands of dollars. So I multiply it by 1,000. That moves the decimal 3 places. So it's $1,003. So that's the idea. And what I'm going to do, well, you guys probably don't have the physical book, but if you did, you could just look in the back of the book to make sure you have the right answer. If you're doing it as part of the homework, it'll tell you immediately whether you have the right answer, which is always very nice. So let's see. Let me check this in here real quickly. So it's 1.7, number 59. We'll see if they said anything other than that. They didn't even put in the $3. They just rounded it off to $1 million. So ours is better because we didn't round it off. So it's $1,003. And remember, it's the rate of change. So our prediction would be if we sell, let's reword it this way because I don't want to say one more airplane. If we increase sales from 20 to 21 airplanes, because it means we're doing one more. We will increase revenue by $1,003. That's what we just found. All right. So that's the end of this section. We do have another section to do today, which makes it nice on the tape, because if you don't want to do 2 sections today, you don't have to. You can just come back later and watch the next section. The next section, though, is really pretty easy comparatively. So the section's 1.8. Notice it's the last section in this chapter. It's called higher order derivatives. And so all this means is derivatives of derivatives. And so I'll do a couple, I'll show you some notation. We'll do one application. I'll talk about what something means. Oftentimes the higher order derivatives, it's kind of thinking, well, what does this really mean in terms of, say, a business application? But we have a physics application that we will see, but we're not going to go too deeply into it. But here's some notation. So let's say we have the function, the derivative, and then what we would call the second derivative, and then maybe the third derivative. And we can go past there. So if we have the function f of x, the derivative we know we just call f prime of x. Second derivative, f double prime of x, surprisingly, and then f triple prime of x. Anything actually past there, say we had the fourth derivative, it's f, and then you just put a little 4 up here in parentheses. They don't keep doing little more primes. If the function is y, we can do the same thing. We can do y prime, y double prime, y triple prime, y. Leave that there. Y to the 4. We put it in parentheses so we don't think it's y to the 4th power. But the other Leibniz notation, remember that's dy dx? Now for the second derivative, think what we're doing. We've got this dy dx, but we're taking the derivative again. So we don't have another y. We write it as d2y dx2. Now it's not that we're just squaring the x. Remember, those aren't variables per se. But that's how we write it in Leibniz notation. And for the third derivative, d3y over dx3, d4y over dx4. But just notice where that number is. It's not in the same place in each of those. But that's all those things mean. That's just derivatives or rates of change. Okay, so let's do a couple examples. And these are, as I mentioned, these are pretty quick and straightforward. Here's problem 6. And what it says find d2y over dx2, which we know just means find the second derivative. The problem is y equals 4x squared minus 5x plus 7. So we y dx, and we get 8x minus 5. And then we take the derivative of that. We write it as d2y over dx2. And we get 8, and I'm done. Much easier than the last section. Let's make that look like an 8 so you don't think that was an 18. And that's it. So not too bad. Let's do problem 10. Same question. Find d2y dx2. Y equals x to the. Well, notice I don't have to use the quotient rule there because I don't have an x on the top. This is really just x to the negative 3. Now I can just use the power rule. So the first derivative, dy dx, is negative 3x to the negative 4. I drop that by 1. The second derivative, d2y over dx2, negative 4 times negative 3 is positive 12x to the negative 5. That's my answer. If you wanted to write it as 12 over x to the 5, you certainly may. But note x to the 5 that goes to the bottom is that negative 5 only relates to the x, not the 12. So the 12 stays on top. All right. So again, pretty quick. I only have 3 more problems and we'll be done. And these next two, again, pretty fast. I just want to show you different types of these. They give us f of x equals x to the 1/5. And the problem says find f double prime of x. So again, just another way of saying the second derivative. Well, f prime of x is 1/5 x, and 1/5 minus 1 is negative 4/5. There's my first derivative. And so my second derivative, negative 4/5 times 1/5 is negative 4/25. X to the, and then negative 4/5 minus 1, or negative 4/5 minus 5/5 is negative 9/5. And I'm done. So again, pretty quick, but I wanted to show you some with some fractional exponents. In case you're curious what that looks like, that'd be negative 4 on the top. The bottom is 5, 25. The 5th root of x to the 9th. And it's the 5th root because that 5 in the denominator of the exponent. And then the 9 is just x to the 9th, and then it's on the bottom because it was a negative exponent. So I would assume, especially since the original problem said x to the 1/5, not the 5th root of x, that the computer would accept that first one as the answer. If I was hand grading the test, I would accept either one as the answer, but most people would just leave it that first way. Okay, this next one, equally quick. problem 30, it says y equals x to the fourth. But it says find d4y over dx4, which is the same way as saying f4x. Now, they're not going to say that because they didn't call it f of x. They called it y. But they could have said y4x. That would have meant the same thing. Okay, so let's go through the steps. dy dx, so my first derivative, 4x to the third. My second derivative, let's just put it here. d2y over dx2, 12x squared. So that one here. Don't put equals there because this doesn't equal that. But if you put an arrow, you can say, oh, here's the next step. d3y over dx3, 24x. And then we'll just say here, d4y over dx4, 24. Ta-da! So a lot of times the higher order derivatives are not that bad. But let me do this. I'm going to give you an application. I'm going to go grab it real quickly. It is in here. Here's my problems. And it's 1.836. We'll just copy that. Move that over. I'll put it right here. Now, here's an application so that I can kind of show you what these things mean. It says, given S of t is negative 10 t squared plus 2t plus 5, where S of t is in meters and t is in seconds, find each of the following. Well, from physics, S of t is position or distance. V of t is velocity, sometimes called speed. But think of what velocity is. It's how quickly your position or your distance is changing. So this is change in distance or position. Well, that's going to be S prime of t. It's the derivative. It's the rate of change of your position. It's how fast you're moving. A of t is called the acceleration. And that is the rate of change in velocity. Velocity, remember, is your speed. So think about being in a car. Am I increasing how fast I'm going? I'm accelerating. Am I decreasing how fast I'm going? That's deceleration. It's just negative acceleration. So that's the derivative of velocity, but that was already the derivative of position. So that's the second derivative of position. So there's an example where the second derivative actually means something concrete that we can talk about. It's the rate of change of how fast I'm going. So it's the rate of change of my position or my distance. So for part A, V of t is just S prime of t. So it's just the derivative of S of t, which is negative 20t plus 2. B says, what's acceleration? Oh, that's the derivative of velocity, which is the second derivative of position, which is just negative 20. So there's my answers to A and B. Those were awful darn quick. And then it says, find the velocity of an acceleration at t equals 1. So for C, my velocity, that means how fast am I going after 1 second? Well, it's negative 20 times 1 plus 2. So negative 20 plus 2 is negative 18. And that's in meters per second. my acceleration after 1 second is just negative 20. There's no place to plug in the 1. I just keep the negative 20. That's in actually meters squared per second. But that's it, a nice quick example. Now, if it's negative, it just means maybe they're looking at direction in this case. So if I've got a negative velocity, maybe I'm going to the left instead of the right, or down instead of up, or whatever they're talking about. However they're ranking that, and my velocity also negative, so I'm going even more in that direction, whichever direction that is. I'm going even faster. Okay, so anyway, we are done with both of these sections. Hopefully that helped out. Again, as always, practice, practice, practice. Watch the video as many times as you need to. Ask me questions during the live session. And that is it for today. Hopefully that made sense to you. And I will see you all again, hopefully very soon.